All right, guys, so we are going to actually add to our page from the other day. So deductive reasoning, our law of syllogism and law detachment. So that was kind of a long one. I didn't want to make it any longer. And on page 18, we talked about these different laws. So the laws are helpful to connect your thoughts so that I can move from one true statement to the next, to the next, to the next. And like the law of syllogism is a really good example of that, because when I have a whole bunch of if-then statements that I can connect the conclusion of one to the hypothesis of the next, then I can make all of these new conclusions. So I can prove new things to be true. Now, that's important to have our connectors. The other thing that's important, though, is to have some math facts or true mathematical things that we can use as our foundation of our deductive reasoning. Okay, so again, inductive reasoning, we use these examples to kind of make a guess as to what we think might be happening, but we need to use deductive reasoning, our laws over here, to come to new conclusions. And the deductive reasoning needs to be based on true math facts. So in terms of geometry, some of the true math facts that we already have are the segment addition postulate. Postulate is just a fancy word for math fact. Or the angle addition postulate, which again is just a fancy word for math fact. We actually have the linear pair postulate, or linear pairs, that's actually a postulate. But we also have some other properties that are very useful, and that's what we're going to go through right now. So I think the next thing that you have is actually this right here. And with this one, I'm actually going to cut it in half lengthwise. If you notice, these 9 squares at the top, or rectangles rather, are the same as the ones at the bottom. So I really don't need all of these. So I'm just going to cut it in half lengthwise. And then use the bottom half as like scrap paper. Gosh, I want a clever way to like fold this so that it'll fit. But I'm going to hold on to that for just a second. And then the next one we want as well. And that one too, if you notice, the same. So I'm just going to cut that in half and use it. Actually, that's a good way to do this. I'm glad we thought that through. Okay. So with this one here, I'm actually going to fold this in half. So I'm going to drop it down and fold it in half. And I actually want to tape this one on page 19 towards the top. We'll write like something on the front of it so that we know what it is. Oh my gosh, I totally taped it on there for kids. Oof. And then this one I'm going to fold in half this way so that I can fit these both on page 19. And then tape that down there. Okay, I love it. Perfect. Okay. So what we have underneath here are all of our different properties of equality. So let's label that. Properties of equality. Now we can use these properties of equality as true math facts to help us prove that other things are also true. So true math facts to help prove something is true. Something else is true. Okay, so if we open this up, the first, actually, you know what? I want to work from the bottom up, because the bottom, we actually know some of those already. So the first property of equality that we have, or property math fact that we can use, is actually the distributive property. So hopefully you remember that. We've talked about that a couple of times. And so if we have something like 2 parentheses x minus 1, then we know by the distributive property that we can say we get 2x minus 2. So if we were to see something like this written down, 2 parentheses x minus 1, then we can conclude that 2x minus 2 is our new statement. The reason that I am able to do this is because I understand the distributive property. Okay, another one that you're probably familiar with is the substitution property of equality. So if, for instance, I know that x is 2, and I know 2x minus 1 is 3, then because of the substitution property of equality, I'm able to replace x with 2, and luckily that is a true statement. 2 times 2 minus 1 is 3. And that's true because of substitution. We replace the x with the 2. Substitution is allowed. It is a true math fact. Another one that you probably know is the division property of equality. Now, this one is a little interesting. So if I have 6 times x equals 3, then by the division property of equality, I can divide both sides by 6, and x will equal half. Right? Because I divided this by 6, I divided this by 6 to get x alone. So the sneaky thing is like when I'm looking at the problem, it looks like multiplication, but I'm describing what I'm doing to solve. Okay, so then I'm able to get half because I divided 6 on both sides. Similarly, we have our multiplication property of equality. So if, for instance, I had x over 2 equals 7, then by the multiplication property of equality, I can multiply both sides by 2, and x would be 14. So times both sides by 2. So these are all like the math facts that we use to solve linear equations, which is super good to keep in mind. Next, our subtraction property of equality. So if we have x plus 3 equals 1, then by the subtraction property of equality, I can subtract 3 both sides, and x would be negative 2. Okay, up here we got our addition property of equality. If I had x minus 7 equals 10, then by the addition property of equality, I could add 7 on both sides, and x would be 17. So again, with these ones, it's kind of weird because like you see subtraction, but what you're doing on both sides is addition. So that's why it's by the addition property, and similarly for subtraction. So it's kind of opposite of what you see, but it's actually what you're doing. Okay, so then these top ones are kind of new and weird. Now the transitive property I really, really like because it's very similar to our law of syllogism. So if I know that like x is equal to y and y is equal to r, then we have these two same things here, I can say that x equals r by the transitive property of equality. So again, we kind of have those connectors like that law of syllogism thing. So that's kind of cool. Like these two things match up. And so we just say the other things are also equal. So that's kind of nice. Our symmetric property of equality says if, let's say for instance, x equals 6, then I could also say that 6 equals x. So we can swap things around because I know sometimes we don't love to see x on the right like this. So we might want to swap it around and it's equal either way. And then the reflexive property is actually super weird. If I have, I don't know, this is kind of strange. I'm going to do it with a geometric thing because it's not really used with numbers so much, but if I had like an angle A, then it is equal to itself. And I should truly put the measure is equal to its measure. Which, like, why would you ever care, I guess? If I have an angle A, its measure is equal to itself. Like, it doesn't seem super useful, but it actually will be kind of useful later. So just saying the same thing is equal to itself. All right, so then down here, we're going to do a little practice. So we'll say that these are our examples. We're just going to go through and we're going to label each one as its justification. So if we open this up, if I see something like this, so if I have LM is equal to OP, and then OP is equal to LM, we're just trying to figure out which property of equality that is. And what I noticed is these swap spots, and that is our symmetric property. So symmetric property of equality, because I'm lazy, POE. So next, working our way down, if we know that M is equal to 12 and Y is equal to 12, then M is equal to Y. So that's kind of like that syllogism thing where I have two different things equal to the same thing. So therefore they're equal to each other. That is our transitive property. The way that my math teacher always explained it to me is you kind of have like a train connector. So in a train, like the cars or whatever connect, and you have that connector right here. Like these are the same, and so they kind of just connect up and join the M and the Y. So train, transitive, and help me remember it. Next down here, if we have 13k plus 20 is equal to 30, then I can do that 13k equals 10. So what I noticed there is that there was a 20 and now there's not. And this was 30 and now it's not. So we must have subtracted, so subtraction, property of equality, because we subtracted 20 both sides, because we're trying to solve for k, I guess. Okay, so up here, if 10k minus 2 is 12, then 10k equals 14. So again, when I compare here to here, what looks like happened is they got rid of that 2 by adding it. So this is the addition property of equality. All right, moving right along. If we have 3 parentheses y minus 6 equals 21, and then we say 3y minus 18, well, that looks like they distributed. So the distributive property of equality, or really just property. I guess you can put property of equality, doesn't really matter. Okay, next, if we have 5k plus 7z equals 12 and k equals 2, then 5, 2 plus 7z equals 2. Oh, I see. They took the k out, put the 2 in. That's substitution. Substitution, property of equality. Is that a property of equality? Yeah. And then next up here, if we have a point z, then that location is the same location. So it's kind of strange to say, is that weird one. That is the reflexive property. Okay, if 12x equals 36, then x is 3. Well, yeah, that's true. And that's, I think, because we divided 12 on both sides so we could get x alone. So division property of equality. I feel like if you've been counting, we've gotten almost all of them except for. So if b over 3 is 6, then b is 18. Looks like we multiplied 3 both sides. That is multiplication property of equality. Okay, hopefully that feels super easy. We'll practice more in class tomorrow.